All right, good morning, everybody. Good to see you all. I wanted to mention before we get started that, and I've mentioned this before, but it's not going to appear in your Moodle for a little while, but I want you to start thinking about it. If if your quizzes aren't going so well, if your grade's not where you want it to be, do consider doing this optional creativity project. It's talked about in the syllabus, and I'll publish the rubric later, but the basic idea is pretty simple. If you have, and I'm sure you do, some sort of creative outlet in your life, it doesn't matter what it is. Maybe you write, or you paint, or you doodle, or you make comic books. If you want to do something in some way pegged to something that we've talked about in this class, which is pretty much everything in the universe, do that and submit it, and it's potentially worth a pretty serious chunk of points. I think it's worth up to something like 10% of your final grade if you do that. So you can bump your letter grade up an entire block, essentially, from like the B to an A or worse. Depending on how much effort you put into it, I'll score it based on that, and it's usually pretty obvious. So does anybody have any questions about that? I want you guys to start thinking about it. It's also a good option if you've missed classes and you're worried about that, because the attendance is also worth something like 10% of the class, or participation, however you want to look at it. Yes?
Is it possible to see any work from previous students on this project?
Ooh. Let me see what I can put together. That's a good idea. I've had like short stories. Someone was into photography and made a cool time lapse of the sky one time that was pretty awesome. I've literally had everything under the sun. It's really open-ended, and it's more just, if you start messing around with it now, you have, I think, about a month left in this course. So, there's plenty of time to just peck away at it every week. And whatever it is that you do, just submit something. And you can submit it directly to Moodle, or you can I'll make a Flipgrid too if you want to put a video up. But I'm pretty generous with that. I think we all really like expressing our knowledge in different ways, and so this is a good opportunity for you to do that. That's completely up to you. If you have concerns about whether this will work or that'll work, just talk to me or email me. Anybody? All right. Another thing is I recently got invited to give a talk in Minnesota during the week. We have a class that I'll miss, which is March 5th, I believe. I actually have to I was thinking, well, I'll just do this class remotely that day. I actually have to talk at the exact same time as this class, which is really annoying. So I haven't quite figured out what to do about that. If anybody has great ideas, please let me know. Maybe I was thinking I could just record the lecture to YouTube, but probably no one will watch it. I don't really want to have to reschedule the class because everybody's schedules are so different. So that seems impossible. Anyways, I need to figure out what I'm going to do about that, and so I would appreciate it if anybody has any bright ideas. We could skip that lecture altogether, but I don't want to shortchange you guys. I mean, we wouldn't skip it. We could cram it into the next one on Thursday, but that seems a little difficult as well. So anyways, I'm soliciting ideas, and I'll tell you the week before again, and I'll send an email so that you don't come into class that day. But I'm sorry about that, but it's actually a really good opportunity because it's the biggest physics conference in the world, essentially. And I got invited to give a talk, so I'm really excited about that, and I just can't miss it. So I'm sorry, but I'm gonna have to let you guys down that day. So think about it. Think about what we could do to make that up. I'm not sure. Okay. Otherwise, let's get some participation points. Again, if you wanna, I'll tried really hard. If people have started participating in class, I really appreciate that. If you have questions as we go through this stuff, raise your hand. I will try to ask you, or tell me your name too when you do that, so that I can mark you down for participation points in lieu of this review that we do at the beginning of class every time. Okay. let's see, I'm really glad you brought that up. I actually think that's one of the most interesting things that's happening right now too, is this changing paradigm. It's kind of hard for you guys to see because this is all happening before your eyes, but when I was in college, there was this very standard idea that all these planets form in place and so forth. And it's just really exciting to see so much on the move right now. And this is one of the ideas, and we're going to keep touching on this, is that, most stars aren't big enough to collapse into something violent like a supernova. And we're going to go through the different types of supernovas today. But most of them are thought to, they turn into these white dwarfs, which is, there's some interesting possibilities there. Maybe they don't. But if they do turn into white dwarfs, as the standard model will have it, then after billions of years, they're just going to cool off. And the interesting thing is when you cool off a white dwarf, you end up with something that looks like a rocky planet or a moon, maybe something like Mercury, something like that. And so the question becomes, well, is that a reasonable solution to our planet formation problem? Because, we've talked about this before, but forming a really dense planet like our own by accretion is subject to a number of serious fractures in reason. In particular, getting little pieces of pebbles to stick together is very tricky. Then also collapsing the thing down. Now, at the center of a star, you have a great amount of pressure to get something super dense like the Earth or like one of these rocky moons, something like that. So it's a cool option. The problem is that the cosmology constrains the timeline, like you said, to 14 billion years, which is hardly enough time to do much of anything, let alone cool off a star to the point of being anything like a rocky planet. So it's still outside the bounds of what astrophysicists are working on, but they're in some sense informed by the cosmologists. And cosmology is a brand new science, actually, and it's kind of interesting that cosmology is even a science at all, because it's always been a philosophical domain for the most of history. So that'll be interesting where that heads. And actually, it kind of brings up this bigger point, which is like this hierarchy of sciences, which is quite interesting. The biologists, if you're studying biology and you're studying something like the mitochondria, and let's say the production of ATP, and you go into the electron transport chain, and you start studying that, and you're trying to make sense of it. Well, at some point, you're going to be like, well, what the heck is an electron, and how does this work? So you go to the physicist, and the physicists tell you, well, the electron behaves according to these mathematical models here. This is an equation for an electron. And you're like, okay, I understand this is an equation, but what is the electron? And they say, well, that's not our problem, that's a philosophical problem. So there's this really interesting void, and the same thing happens in planetary science and astrophysics, because there's this hierarchy again where the planetary scientists go to the cosmologists, who are the mathematical physicists in that domain, and say, well, could this happen? And the cosmologists say, well, we don't think so because, the age of the universe is constrained like this. So in some sense, all of the different sciences have this strange bottleneck at the mathematical physicists, where the mathematicians in our current culture are the ones that have all of the power. And I think math is extremely powerful, but it's taken this interesting seat where the math itself is fundamental as opposed to the math telling us about the physical reality. And so this is something I'm really interested in exploring, and I'd be curious to hear thoughts about this. But it's also something I'm working on a book about right now, because it seems to have happened at some point, when somewhere around the time of Galileo to Descartes to Newton. Newton was actually the first person Newton's probably the biggest hero of physics right now, and has been for quite some time. He, of course, gave us this law of universal gravitation most famously, did a bunch of work in optics that are holding up to this day, more or less. But Newton made this really interesting caveat at the end of his piece. He actually attached an addendum to his magnus opus. And he said, I've provided these laws for how gravitation works, but I don't mess around with the cause of that gravitation. And furthermore, it's not the job of the physicist to do that. Which is interesting, because then you got to say, well, whose job is it to figure out the cause of these phenomena? Whose job is it to figure out why gravity works? And so this tradition is set up, and we're going to get into it in the back half of the lecture today. General relativity comes along. It actually improves on the precision of Newton's formulation of gravity, but once again, the more closely you look at it, the more you realize that it's just a very accurate mathematical description of the way that events unfold. It doesn't actually give us a cause for gravitation. And of course, the popular media has reified the math into something approximating a material explanation. You know, they'll talk about the fabric of space-time. But in reality, as we'll see, that's actually kind of a poetic analogy. They don't act, you know, relativity says nothing about the material basis for gravity. And so there's a really, really fascinating void there. And there's other voids. And in some sense, it's due to this hierarchy of people answering to these mathematicians at the end of the day. And the buck stops there at the mathematicians. And so, in some sense, I feel like punching through that mathematical layer at the basement of all of these sciences is going to result in an enormous scientific revolution at some point in the near future. Well, hopefully near future, I think. However, it's one of those interesting problems that people keep tossing back and forth. Nobody wants the problem. The physicists say it's a philosophical problem. The philosophers say it's a physics problem. I actually had this really interesting occasion. I wrote this piece about this. I just was writing some blogs a few years ago before I started the podcast. And I put this blog on our physics about this essential problem, that math was basically a very highly accurate description of reality, but it wasn't an actual step-by-step explanation for any process. And in fact, you can't put an equation on the board and have it explain anything without putting a bunch of English next to it to tell you what the variables mean and how the reaction proceeds. And it was kind of rocketing up the chain on this Reddit, R Physics. And then all of a sudden, the R Physics moderators pulled it. They said, we can't have this here, this is philosophy. Well, I said, okay, great. So I went over to R Philosophy and I posted the same blog. It was rocketing up the R Philosophy chain. And then the moderators pulled it and they said, this is physics, not philosophy. So it's a really interesting hot potato that nobody wants. And I think there's something really valuable there. And it's kind of at the center of all of my own research and all the work that I do. So it's going to keep cropping up. And I think that this idea that you bring up, Ethan, about the constraints on our imagination with respect to what can happen is in some sense guided by the same mathematical mindset, which is that we trust the math and its implications beyond our own even rationality at some level, which is really, really fascinating. And it makes sense because math has, you know, given us incredible technologies. It's really good for building spaceships and cell phones and things like that. So why shouldn't we put our faith in it? And the question is, well, how far can that take us? You know, what happens when we believe in something to the point of ignoring basic physical reality too? All right. Let's see. I think I'm almost through this list again. Okay. That's something that's really interesting. I'm going to talk more about that when we go through the supernovas today. But it is really interesting that the popular imagination is really fixated on supernovas and these really destructive, violent ends of stars. But then this ties into what you were talking about too, right? Most of the stars don't seem to end in supernovas. In fact, they seem to be rare enough that we haven't even seen one in our own galaxy, or at least one that's visible. You know, people will point to maybe one happened inside of this cloud of dust. Maybe this thing over here is a remnant of a supernova. But in terms of people actually having seen one since the dawn of telescopy, like modern telescopes essentially, nothing. So that's really, really interesting as well, especially because so many, and we're going to move, like next, on Thursday, we're going to start talking about black holes. And black holes are, of course, like one of the most tantalizing subjects in all of astrophysics. And almost anything that doesn't make sense that we see in the sky at this point is attributed to a black hole. You know, objects orbiting something that they can't see, it's a black hole. You know, jets terminating in a point that doesn't seem to be a star, it's a black hole. There's the galactic rotation doesn't make sense. Well, there's a black hole at the center. And it really opens up this whole window as to what does this word black mean in astrophysics. Also dark, right? We see dark matter. I mean, we'll get into this with cosmology, but in order to actually have gravity be the fundamental operating principle for the universe, we have to plug in something like 90% of the mass of the universe and just imagine it's there, but we can't see it. They call it dark matter, or I guess the more dynamic version being dark energy. But those are things we haven't observed, and the same, I'll make the case to you, the same goes for black holes. It's just a matter of trying to put a hole, fill that hole in our theoretical understanding. So I urge a lot of caution when we see these words dark and black, because they often mean something that we don't understand, and we have a placeholder sitting in for them. So, very good. All right. Yeah, so one of the interesting things is that we gauge the age of these stars largely by their location in these clusters and so forth. And of course, our own galaxy, by evidence of our own solar system and our own planet, seems to contain a lot of materials, all of the materials in this room, basically, with the exception of hydrogen, seem to necessitate something more powerful than our own sun, or something like a collapsing ball of hydrogen, right? So where did all this stuff come from? And the thought is that, well, our sun and our solar system was assembled from the remnants of several generations of other stars. And of course, the bigger a star is, the more heavy elements it can make, but also the shorter it lives because, it's crushing itself more quickly. It burns through its fuel more quickly. And so the thought is that there has been time in the evolution of our own galaxy to create all of these elements. So yeah, that's quite interesting. All right, let's keep going. So let's review what I kind of got stuck in the middle last time of a thought. Let's just review this white dwarf business, because we kind of ended on neutron stars, but neutron stars are essentially a special case of the white dwarf. Anybody want to point that out for me? Anybody have a good recap on what white dwarfs are? Okay, well, I'll do it for you. Okay. In some sense, I think that this is a really important moment, because white dwarfs are sort of the gateway drug to broken physics in my perception. So white dwarfs are this moment where we take a body that's collapsing under its own weight, and it collapses so much that it no longer behaves as normal matter. Now, it's interesting, too, I think that this is worth pointing out, that the reason that we're able to use these physical equations to describe a body that collapses to the point that it's completely dissociated is because we treat those stars as ideal gases. Now, it's well understood that liquids and solids are by definition incompressible, particularly liquids are incompressible, right? This is the basis of hydraulics technology. You can squish it all day long. There's nowhere for it to go, right? It's already condensed. So if, I've sort of made the case for you that there's a really decent argument that at least the photosphere of the sun, based on its continuous spectrum, is something a bit more like a condensed matter, something more liquid-like with a transient lattice that allows it to give that continuous spectrum very different from these gaseous lines that we see, right? Well, the problem is that's a difficult pill to swallow, because if the suns are actually in some sense a more liquid metallic hydrogen type of material and they're not gases, then this entire story of white dwarfs that I'm telling you goes out the window, because you can't actually collapse something that's made out of liquid. That means no white dwarfs, at least that doesn't mean we don't observe very hot, low luminosity stars. And it doesn't necessarily mean that the result of the death of stars doesn't still produce something that's low luminosity and very hot. That's certainly possible. But the explanation for it being this exotic form of matter that's collapsed goes out the window completely. And of course, everything after that, black holes and everything else, goes with it. So it's a really disturbing conclusion to hold in one hand, and then to also explain this standard story to you on the other hand, because as far as I can see, I don't see any way that we're going to be able to, in the long run, hold on to the idea that the sun is a ball of gas. Just, the most basic experiment that you can all do with a simple prism right now would sort of dissuade you from believing that that's the case. At any rate, the standard story goes that these gaseous stars, under the basic ideal gas laws, are able to collapse, and there's so much heat as this happens that they dissociate. The atoms stop even making sense at some point. And so we think about them as these just, homogeneous goops of, atomic building blocks, essentially. If there's so much mass, then they collapse beyond this degenerate electron gas phase of the white dwarf, and they actually become a neutron star, where essentially the neutrons are now this is the nuclei of the atoms are just squished together into one homogeneous substance with, billions of times the density of water, just an unimaginable density. So that's the white dwarf, that's the neutron star as well, being an extremely dense version of that. Now, the result of that is a few possible catastrophic outcomes. So we've talked about how when basic stars like our own die, and I think like a bigger version of our own, Betelgeuse that we talked about in Orion is a more visible version. It's shedding layers of its external skin, let's say. Its outer layers are being shed as it goes through these different flashes of fusion throughout its onion-layered structure. Now, something interesting happens in these really high-mass stars, at least this is how the theory goes, that when that neutron degenerate core, it's able to sort of, at some point, resist the further collapse. So the neutrons can't be compressed any further, is how the theory goes. And there's this sort of jolt that happens when all of that electron degenerate material of the white dwarf has kind of condensed down as far as it can, and it reaches, let's say, a wall where it can't push against this neutron matter anymore, this degenerate neutron matter anymore. And there's a sort of shock that happens when it hits that wall, sort of like crashing a car into a tree or something. So when this happens, there's a great deal of energy released in that shock wave in the form of a very interesting kind of radiation called neutrinos. The neutrinos, the power of these neutrinos is enormous. So it's something like, 10 to the 46th watts in these collapsing stars, which is greater than the power put out by all the stars over 1 billion galaxies. So that sort of stretches the imagination as well. Now, ordinarily, neutrinos don't interact with regular matter, but that matter is thought to be so dense, right? We've created this model where the matter is something like 400 billion times as dense as water, that there is actual interaction between the neutrinos and the matter in these ultra-dense white dwarf neutron stars. So they push backwards on the outer layers of the star. And this huge sudden input of energy reverses the infall, the gravitational collapse of these, and the result is a supernova. And what's left over is just the hot core of that, which is called the neutron star. So this is a pretty fantastical story, and there's a couple of types of supernova that are thought to result from this. Now, bear in mind, these are really exciting ideas, but they seem to be quite rare in some sense as well. So the first one I want to talk to you guys about is the collapse of a really massive star, this process we've been talking about. For historical reasons, that's called a type 2 supernova, when a star simply goes through this process because it's so large that it has this shock wave as a result of compressing against the neutron core and explodes. So these are some pictures up here, 5 different supernova explosions from other galaxies. The bottom row shows the host galaxies before and after the exploded stars. All these are thought to have happened many billions of years ago. The explosions from these supernovae are thought to outshine the entire galaxy, so very, very powerful. And of course, this is where we believe that we have the energy available to actually fuse these enormous heavy elements. Might be so. In fact, probably is so that if you had an explosion that large, you could certainly fuse these really heavy elements. You know, things like the metals that we find in our world, particularly the really heavy metals. But there's, like I said, I've brought up Cebulski's star before. There's evidence that perhaps this is happening in more ordinary, mundane ways in the outer layers of stars as well. And I think this lattice-confined fusion is a really intriguing possibility for that. So, as you can see, the fate of a star really depends on how much material is there. That's a really guiding, I think that's a reasonable guiding principle for our story of the life and death of stars. What's interesting is that you're going to start to see, and I'm really making the case to you throughout this course, and I think this is how the science is progressing, that the planets and brown dwarfs kind of fall on this continuum to some extent, right? So we traditionally haven't thought about planets as forming on their own independently of star systems. But that idea has been stretched quite a bit by this new James Webb data, where we see these co-orbiting pairs of Jupiters. So in some sense, there seems to be a shared mechanism where you get enough stuff in one place, you have big enough kernels through chemistry, condensation, whatever it happens to be, you end up with a planet. If it's a bit more stuff in one place, you end up with a brown dwarf. A little bit more, the fate of this thing is going to be a star that eventually transitions into a white dwarf. And then, you know, all the way down the line until you're essentially big enough that you're collapsing into something like a neutron star, which is the result of these supernovas. And we do see evidence of the remains, well, at least what is interpreted as the remains of supernova explosion. And I think that's quite valid because at least there have been some recordings in the historical record going all the way back to the Sumerians of supernovas that have occurred. The most recent one was in Galileo's time, shortly thereafter, 1604. And it was apparently quite a sight to behold. It was something like an enormous star being completely visible during daytime for people in Northern Europe. So it was really incredible to see, from what I understand. And people have actually been able to go back and find the remains of this supernova as it was left over with modern telescopes. They've been able to see it in different wavelengths. So what we see here is this bubble-shaped shroud of gas and dust, which is about 14 light years wide and expanding at 2,000 kilometers a second. The energy or the light that we're actually seeing is visible in X-rays. That's in blue and green, and there's some visible light in yellow, but you can see the visible light has faded quite a bit, and into the infrared, which is in red. Now, it's interesting because the expanding shell, this is another interesting point. So the expanding shell of these supernovas appears to be super rich in iron. And so it really, and I'll show you another picture here in a second that brings this point home further, but it seems like just the big explosion seems to have a lot of iron in it, right? The expanding shell of dust and debris. You know, I've put this in front of a number of my astrophysics friends, and it seems like there's a reasonable possibility that there's chunks of material that, and I pointed this out to you when we looked at the layered structure of these heavy, high-mass stars right before they go supernova, right before they collapse into white dwarfs. They have this layered structure that looks a lot like a rocky planet, actually. And so, again, going back to the pebble-boulder boundary problem in planetary formation, what if, as these supernovas proceed, you actually get chunks of those really dense stars flung out, and you get these little like seeds, these little cores, right? These little iron-rich, almost very similar to these rocky planets, these little chunks of things. And that those can end up getting swooped up by freshly forming star systems and form the basis for these rocky planets. It seems like a reasonable hypothesis to me. I mean, the magnetism question is a real nightmare, mainly because we have an incredible magnetic field. We talked a lot about this last semester. But Venus is almost identical in composition to the Earth. It has no magnetic field. And the reason for that is perplexing to almost everybody. You know, it's a very difficult question to answer. Now, we have a huge moon. I don't know if you remember this from last semester, but our moon relative to the size of our planet that ratio is enormous compared to most planets. So you think about the other planets we talked about with moons, like Jupiter, Saturn, tons of moons. But Jupiter and Saturn are enormous compared to the Earth. And their moons are, you know, about the same size as ours. So we have this huge, huge moon that's whipping around our planet. Now, could that be contributing to the tidal churning of the swirling of the internal stuff? Maybe, because Venus doesn't have a moon. So, yeah, maybe some of that swirling is set off too, right? So, the idea that a star system would swoop up chunks of a supernova's remnant, it's already in place in some sense, right? Your textbook goes through this whole idea of recycling material through, they call it, I forget what they call it, but this chapter on the interstellar medium concerns the idea that these star systems like our own are born of the remnants of old dead stars, right? And we know that's the case because our star can't possibly make iron, right? It can't, and let alone some of the super heavy elements we have, like plutonium on this planet, right, that are freaking enormous. I mean, hundreds of hydrogens worth of material in one atom. Superons, they're so heavy they just can't even hold themselves together. They fall apart. That's why they're radioactive. So where in the world did those come from? So they have to have come from a much bigger star that died. The question is, were whole chunks of that star preserved in its death as well? And so, you know, I guess I'll jump ahead to this picture here, which I find really tantalizing. So this is a supernova that we observed in another galaxy. And what you see here is that these bright spots are actually nickel, an unstable element of nickel that decays into a cobalt. But we know that these same sort of bulbous chunks can be seen in iron as well, and the radioactive iron decays into a stable form of iron. So we got lots of nickel, lots of iron, basically all the stuff that is heavy and dense and very difficult to explain its production underneath our feet right now, that flies off of these supernovae. So let me make sure I had nothing more to say about these. Okay, we'll move on from that. But the idea is that on average, like according to these theoretical predictions, we should have a supernova every 25 to 100 years. Problem is we haven't seen any. So what's up? Are they hidden? Is the model broken in some way? We'll see. Time will tell. You know, supernovas, the reason we call them type 1, type 2, these have a lot to do with their spectra, and I'll get into the details of that. We've been focusing on this type 2 supernova, and I'm going to continue with that. All right. Now, supernovas have this very particular decay curve, too, and the idea is that if supernovas really have a signature, the way that they unfold, the brightness, the decay of the brightness, that if that's very standardized according to that mass relationship we were talking about earlier, where, you know, the bigger ones have these more violent supernovas, they have this very standard decay curve. The cool thing is, and we'll talk about this in a later week, that we can use that to expand our distance ladder that we set up originally, because we can say, oh, in this other galaxy we saw this exact same type of supernova, therefore we know how big the stars are in that region, therefore we know how far away it is because we know its absolute luminosity. So these decay curves are going to prove quite useful to us later. Now, the inevitable product of one of these type 2 supernovas is this neutron star. And there was a woman named Jocelyn Bell who was at Cambridge University in the 60s studying these distant radio sources. And she found a really strange radio signal that was different than something that anybody had ever seen before. And it was this kind of like periodic blipping sound, let's say, for a radio signal. It's kind of this oscillating, like a turn signal. And what she deduced, or at least what she proposed, well, first, people played with the idea that it was aliens, of course, just like everything else. But eventually, through continued discussion, people decided that this was actually a neutron star that was spinning very rapidly. And of course, due to the same processes we've talked about in the formation of stars, where you have a very different, you have these jets coming out of the top of these stars, out of the poles, where essentially the material is moving slower than at the equators, so it's essentially a place there isn't a ring of dust being flung off at the equators, and so you channel all the material, all of the radiation out of the top of it. The same thing they believed was thought to be happening with these neutron stars, except as the radiation shot out of the top of these neutron stars, they were precessing very rapidly, and so you got this, and I'm talking like on the order of, believe on the order of seconds, how fast these things are spinning. Really, really fast. Gazillions of kilometers per hour in revolution speed. And that's generally the accepted idea for what a pulsar is. They call these pulsars, is that it's a spinning neutron star. Now, like I said, if the stars aren't actually made out of gas, then they can't actually collapse into anything like a neutron star. And so alternative explanations will be necessary. One possibility for these pulsars, which is quite interesting, is something a lot more like your turn signal. So does anybody have any idea how your turn signal works? Sometimes you get like a car person in the room. It's a special type of electric circuit called a relaxation oscillator. Okay, which is actually a really simple circuit that essentially involves, it's sort of like you're shorting the circuit with a capacitor, and without boring you guys to death, the basic idea is that the capacitor can, you have a diode, so a material whose conductance changes depending on how much current it's receiving. And so what it does is that as it gets more current, it actually becomes more conductive, which overloads this capacitor. Capacitors are kind of like mirrors for electricity, so they kick the electricity back into the system, and the result is that you have a diode, like an LED type thing in a bulb, that's basically flickering on and off as it becomes overwhelmed and then discharges, the capacitor discharges, and then it builds back up the current and then discharges. So you get this perpetual, by just applying a current to this system, you get this perpetual loading and discharging of the system, and the luminosity changes as a result of it. So this is actually a really common phenomenon in nature. There's a lot of these very simple relaxation oscillators. Your heart actually works in a very similar way to provide this very steady pulse capacitively through the neurons or the electrical cells that are working in your heart. So there are other physical means by which you could get a very fast blinking light, let's say, occurring, changing the actual structure of the atom, or of the star. A lot of this theory that I'm bringing up, though, has to do with the basic acceptance that there is a material lattice structure to the stars, and that lattice structure would change the optics of the situation, as one would expect with any other material. Remember, a piece of a diamond and a soot-covered box are the same atomic composition. They're both made out of pure carbon. But they have very, very different optical properties, right? And that's simply a matter of the geometric way in which those atoms are arranged inside of the material. Of course, these considerations are not taken into account if your star is made out of gas, because it has no lattice whatsoever. And so I just think that, and I'm interested because I feel like if I continue teaching this class for any more years, 5 years from now, we'll have a very, very different story to tell about a lot of this stuff than we do today. This basic principle of the gaseous sun seems to be really on the ropes to me, and I think there's a lot of downstream consequences, including this whole lecture about neutron stars and stuff that is going to have to change wildly. But let's keep going with it for today. So far we've been considering these stars in a vacuum, like a star all by itself, right? But we know most stars don't occur all by themselves. Most stars actually are binary, trinary, quaternary. There's multiple stars orbiting one another, especially during the formation stages, and maybe they drift apart over time. So something interesting is thought to be able to happen in these two-star systems. The fresh hydrogen from the outer layers of a companion can actually, if one star dies, let's say, if it goes through this transition to a white dwarf faster than the other, then it has presumably a lot of gravity in it has a lot of material in one place, right? They're thought to be incredibly, almost mind-bogglingly dense. So they have the ability to actually start siphoning off the fresh hydrogen from the other star. And you get this really kind of hungry hippo situation where the white dwarf is now starting to gorge on all the material from its companion star. So it has the ability to rapidly gain material. And the result of that is that it heats the star more and more, and the surface temperature rises. Fusion actually can be sparked in the outer layers of that star in a very explosive way, which we call a regular nova, actually. So this goes on and on and on, and it continues to consume this material, and at some point it reaches that same cataclysmic moment where an enormous amount of fusion, especially of the carbon that's remaining in that star, takes place all at once, and it results in an explosion. This kind of explosion is actually called the type 1 supernova. So we have type 1s and we have type 2, and I think that this is probably something worth remembering. Type 2s are from the death of the massive stars. Type 2s have to do with the consumption of a companion star's hydrogen. So what more is to be said about these? All right. Now, stars whose cores are less than, let's say, 1.5 suns, by the time they run out of fuel, they're going to end their lives as basic white dwarfs, and the white dwarfs will just cool over eons. When they have masses between 1.4 and 3 solar masses, we think that they become neutron stars. Now, there's stars that are much greater than 3 solar masses, and what's interesting is that these stars completely break the model altogether. And so we'll talk about this more next time. I think on Thursday we will give black holes their due diligence. But this window where you have so much material in so little space really breaks the models and puts us over the limit of what we can ordinarily describe as material reality. So it's an interesting possibility. It's an interesting opportunity to explore what it means to break a model in science, too, and what sort of conclusions result in that, and what it tells us about our world, or versus what it tells us about our model itself. So I want to spend ample time on that, and we'll reserve the space for that soon. One thing that's really important, One thing that's really important, though, before we talk about black holes, is that we make sense of general relativity, which is the updated version of gravitation. So I'm going to spend the back half of the class today talking about general relativity, because black holes, the conclusions that people are drawing about these large mass star collapses only really make sense in the context of A, treating them like ideal gases, and B, making some really liberal conclusions from Einstein's revelations about gravity. So we need to understand Einstein's ideas first. Of course, there's a really boring option for a lot of these stars too. If you have a red dwarf like ours, our own sun, and it goes down, and we think that, okay, it sort of explodes, maybe not so cataclysmically, it goes through this giant phase and then turns into a white dwarf. Maybe so. But what about brown dwarfs, right? What happens to a brown dwarf over time? Well, it just sort of cools off from the beginning, right? And what does it turn into? Well, that's an interesting question. And also, is there a room for you to transition between these two states? I think that that's going to be a really big topic that opens up in the future as well, because I've mentioned it many times, but the difference between a red dwarf like our sun and a brown dwarf at the very threshold really just comes down to the smallest amount of material crammed into the smallest amount of space. So is there room for these stars to transition between brown dwarfs and red dwarfs, and to have different fates as a result of that? And I think this brings up a bigger point that I really want you guys to think about, which is that we've tried to explain this, I hope you guys can see this all right, but you have the main sequence here, right? And we've talked about stars. We've used this diagram to understand the lives and deaths of stars, in that the stars find their way down onto the main sequence and spend most of their lives there for the most part. And then they drift off, become giants. The giants shed their layers, and then the cores collapse, and they head down to the bottom and become white dwarfs. But I think that there's one thing that might strike you as really interesting is that, and this isn't a great diagram to show you this, but most of the stars we see are either on the main sequence or they're in the giant phases, right? There's not that many white dwarfs, actually. Now, you might say that's because we can't see them because they're small. Fair enough. But I don't know. It sort of raises the question of why we don't have equal amounts in each one of these compartments to some extent. But one thing that's absolutely certain is that you can take brown dwarfs and fit them onto this continuum if you extend it down to the bottom right-hand corner, right? They fit very nicely on the same line as the main sequence. And so what I'm trying to open up the possibility for you guys is that there might be a more mundane path for these stars that doesn't involve them, going through all of these violent stages we've been talking about, which is that they just kind of cool off, right? And they head down the main sequence as opposed to off of it. Now, that'd be a very difficult thing to prove because it would take millions of years to see that happen. So no one's ever going to actually see that happen. But needless to say, the brown dwarfs do fit onto the continuum really nicely. Now, I actually saw, to this effect, I saw a really interesting paper that I wish I'd brought up last semester, but it's germane to our discussion of this sort of evolutionary track that's happening. I've mentioned this before. We talked about, I think a couple of classes ago, about this idea that there's a radius valley that people are having a hard time explaining with these Neptune-sized planets, right? Between Neptune and super Earths, there's these mini Neptunes, and there doesn't appear to be a lot of them. And we're actually missing super Earths and mini Neptunes altogether in our own system. Now, these are some of the most common types of planet in the whole universe. But there is this little valley where there's a certain portion of them, of a certain size between Neptunes and super Earths that does appear to be missing in general. So the question is, why is that? And this paper came out that proposes that the reason for that is because actually, due to the size of these mini Neptunes, they don't actually have the gravity to hold on to their atmospheres. And the result is that they very quickly progress from something like a mini Neptune to something like a super Earth and lose their atmospheres as a result of it. And I think I brought it up to you guys before that one possibility is that that something like a Neptune gets really close to the sun and cooks its atmosphere off. And of course, that is still a possibility, but that's thought to happen very early when the planets are still migrating around during the early solar system days. However, this happens like 1 billion years later, right? This, the core, actually, of the planets, this is called core-driven evaporation of the atmosphere. The core is not that big, so it can't hold on to the atmosphere. It's also really hot still from its formation, and so it's cooking it from within. And I think this is just really tantalizing because it brings up the idea that all of these bodies, in some sense, can be envisioned as not necessarily having to do with these catastrophic steps, right? These really violent, amazing, awe-inspiring stories that we've told up to this point. But there's also a really interesting, more boring metamorphosis that might happen as well, where things kind of cool off or evaporate. These very, mundane physical processes that we tend to try to ignore a little bit because, well, they take a really long time, and so you never see these things happening. There's no real evidence of this, right? You're not going to see a big ball of fire in the sky to support this kind of theory. But this did come out in the Astronomical Journal, and it is a increasingly entertained idea. So we'll see how this story wraps up, and I think that there's no faster changing science than planetary science and astrophysics right now. It's really, really exciting. Okay, I need to talk about general relativity next. Does anybody have questions about these catastrophic failures of stars and so forth that we've hit on up to this moment? Thoughts, concerns? It has to be a condensed matter to have a lattice, yeah. So the question is, right. So like everything, all of the solids, everything that's solid here has I don't want to use, I think crystal is the best way to think about it. A crystal is maybe more regular than a lattice in a lot of these amorphous solids, right? So, a plastic might have a network of different molecules that are sort of fixed to one another. That's also a lattice, but it's an irregular lattice. So a crystal, like if you think about diamond, it has a regular lattice to it, right? Now, all of those black body experiments were done with a soot-covered chamber. Soot has a really crystalline lattice to it. It's this hexagonal planar lattice to it. Just a bunch of hexagons tessellating, basically, which gives us this perfect black body spectrum, right? And so the idea, if we want to start thinking about, well, if the stars aren't made out of pure gas, if they do have a lattice, if there's something liquid-like, or they have condensed matter in their photospheres, in their surfaces, well, we might want to think about a lattice that's more crystalline and regular like that, because that's what we see the best black bodies from. And stars, of course, give us some of the most perfect black body spectrums known to exist, known to occur, I should say. Okay. Now, so in order to talk about black holes, which are, of course, the most exciting possibility at the end of these destructive collapses, we have to make sense of general relativity. So what in the world is that? Why are we so in love with it, and so forth? Now I'm going to try, as I go through all of this, general relativity is actually quite an astounding improvement over Newtonian gravity. But of course, I have to reiterate, like I said at the beginning of class, that these mathematical descriptions of reality are far from explanations of reality. And that's something that's left this incredible chasm in our physical sciences that I think that I spent enough time on before. A good way to explain relativity to somebody like yourselves is sort of something like this. Let's say that you go to see the musical Peter Pan, right? And you're sitting in the auditorium, and you see Peter Pan fly in from off the stage, right? Now, let's say that each of you were incredible calculating machines, and you could write down a numeric description of what happens when Peter Pan flies in off the stage, right? Well, I could amalgamate all of your different perspectives from everywhere in the room, and I could find some commonality, and I could create a mathematical model for Peter Pan flying in off of, stage left, right? However, nobody managed to notice that there was strings attached to Peter Pan. And so the strings didn't make it into the mathematical model that I constructed of Peter Pan flying in. And the result is that, people who are wearing these green costumes can fly. That's the conclusion as a result of it. And by the way, we have incredibly detailed mathematical models to show exactly how those people can fly. Of course, they have to be on this particular stage in order to fly. So the stage imbibes them with magical qualities that allows them to fly. And we have incredibly precise mathematics that allow us to predict how they're going to fly, because we've seen this happen a number of times, and we know that people on this stage can fly. Now, can people really fly on that stage? No, like they're attached to strings. But the strings didn't make it into the mathematical conception. So general relativity is a bit like this, It's very good at reconstructing the appearance of what is happening and deconvolving it into mathematical generalizations. It's essentially, the reason we call it relativistic is because we're giving the perspective that you would have over here of the events, the perspective you would have over here, and relating how those perspectives relate to one another. It's all very observer-centric. That's why I put this sort of parable inside of a theater, because it's based on amalgamating all of the different observers' perspectives as to what's actually happening there. There's a fantastic article, I can't remember the guy's name, but I probably couldn't pronounce it even if I could, a Greek philosopher. He tells a similar story criticizing relativity as well, where he says, if you were in a magic show and all of the audience members related to a man sawing a woman in half on stage, everybody could tell you exactly how, in other words, what it looked like when the woman was getting sawed in half. But nobody had any idea that the woman just pulled her legs up inside of the box, and she didn't actually get sawed in half at all, right? But you could still describe it with incredible accuracy and incredible detail. And so this is essentially what I believe that Einstein has done, is he has actually made a really brilliant observation, which I'm going to get into in a moment, called the equivalence principle. So he worked out the equivalence between inertia and gravity. And the results of taking those basic Newtonian equations for inertia and gravity and making them equivalent to one another allowed him to develop a mathematical formulation called general relativity, which is a very, very accurate description of the way that bodies behave when they're in gravitational proximity to one another. And so it's an incredibly powerful theory. It's more accurate than the Newtonian idea, which suffers under some, minor conditions. It also, as a result of this, leads to a number of rather insane conclusions, which we're going to pick apart here as well. Because the way that Einstein depicted reality was he broke it up into a few different variables. He used some of the traditional Newtonian ones like mass, right? And if you think all the way back, what does mass mean? Well, it really just means how much an atom is pulling on another atom, right? But unfortunately, Einstein and maybe Max Planck had something to do with this too. They sort of reified that idea of mass into the same thing as a body, right? A physical body. But mass is really a description of what bodies do. It's not really a thing by itself. Have you guys heard this word reify before? So reify means to mistake a map for the territory. It's like treating some idea, an abstraction, as if it's a concrete reality. So pull, the amount of pull an atom can do is an abstraction. It's not a physical thing. I can't hand you some pull, right? Now, so this basic reification happens in the Einstein equations. Mass becomes synonymous with material body, which leads to some disasters down the road. The other thing that happens is he breaks up reality into coordinate systems of space, right? So this leads to another interesting reification. So what is space? Well, it's just a coordinate system for describing locations in any particular system, right? The problem is that coordinate system gets reified into an actual material. He actually adds another coordinate to the system of space, which is time. So he adds change into the system. And the change becomes reified into this metamaterial called space-time. Now, space-time is not actually a material, but it's very analogous in these equations. And the way that people downstream of Einstein interpreted it was as some sort of fantastical material. Now, of course, materials can't be dynamic, right? So I can very easily describe to you the material properties and the structure of this table I'm sitting on, and I don't need to bring time into the picture whatsoever. It doesn't have to be dynamic. Materials are static concepts. You conceive of them based on their structure and their properties. And so space-time doesn't fit the bill with respect to that. But at any rate, Einstein has set up this conception of reality and gravity that is based on space and time, primarily, and mass as a stand-in for physical bodies. So the whole thing is this very abstract landscape that's very articulate. Again, we can describe exactly how Peter Pan moves on the stage, very, very precisely. But we don't know why. So I think it's worth pointing out to you how he came about this, because it's actually quite brilliant. As I think that it's the job of the scientist to be skeptic. It's often been said, I think it was Feynman who said that religion is the discipline of faith, science is the discipline of skepticism. And so, I obviously have a very skeptical tone about a lot of these things, but I think that the work itself is quite brilliant, in particular this aspect as well. So Newton's two basic equations. This is kind of the reason Newton is a god in science, is because he deduced these two relationships. The first one is inertial. So something that is held in place, its mass represents how it's attached to the atoms around it. So, I'm being attached to everything in this room right now, essentially, as are the rest of you. in order to accelerate me off this table, you have to put some effort into it, right? Something's got to push me out of the way, right? He termed this push a force. That's where we got the word force. Sounds very Star Wars, but basic idea is that it's a push. You can actually have a negative push too, which we call a pull, a tension. But the basic idea is this qualifies inertia. Things want to stay exactly where they're at unless you apply some sort of a force to them. It's a reasonable proposition. It seems to play out, and he scaled it in this mathematical formula. He also deduced another kind of force. He was like, I think that the reason the stars obey Kepler's laws is because there is this force which is proportional to how much material is there, how much mass they have, how attached they are to one another in that particular system. Now, the interesting thing that I feel like Newton could have easily deduced general relativity if he'd just gone so far as to realize that he has two equivalent statements here. The force of a mass system is equivalent to its acceleration, but it's also equivalent to the product of the masses in the system with respect to the distance between them. So these two statements can actually be set equal to one another at some point, which is the really brilliant insight that Einstein worked off of. Now, there's some reason to believe Einstein actually got this idea from this dude named Ernst Mach, because Mach never wrote it down exactly like this, and it became famously known as the equivalence principle. And of course, there's lots of people who are toying with this idea, but nobody processed it mathematically like Einstein did. So Mach had this idea that, wait a second, I think the reason that when I spin around in a circle, that my arms fly out to the side, for instance, that things kind of tend to stay where they are or keep moving the way they are moving, is because they're attached to everything in the universe, essentially. The distant stars, everything plays a role gravitationally in terms of keeping things put or keeping them in motion. And Einstein really just picked up on that idea and processed it mathematically. So without boring you guys, well, there's no way I could even bore you to death with the details of how Einstein processed this equation. But his essential insight was that inertia and gravity were the exact same thing. There's no difference. And once you accept that, and I think he had this thought experiment where, if he's in an elevator and all of a sudden the elevator starts accelerating up and he's standing on a scale, it'll appear as if his weight's gotten larger. The gravity's been turned up in his elevator. You've probably experienced this before. Probably more the opposite, like you're in a plane and all of a sudden the plane goes downward and you feel like you're kind of weightless for a second, right? It's kind of spooky. Or you go over a hill in a car really fast out in the country, right? So what are you feeling? Well, for yourself, you're feeling like gravity just got turned off for a second, right? And so Einstein famously had this thought experiment where he realized that gravity and inertia were really just two sides of the same coin. They're really the same thing. Now, that allowed him to put these equations together, match them together, bring in a bunch of mathematical geniuses who were his buddies at the time, and process those using this brand new kind of tensor mathematics to produce a theory just based on locations, based on mass, and based on time for essentially how all of these bodies in the cosmos would behave based on these very simple dimensions, let's say, very simple variables. But the one thing that he never went so far is to think about, and nobody's really done this yet to my knowledge, although there's some people working on it. Again, brilliant formula. But what's doing it? What's allowing Peter Pan to fly through the sky? Why is it that gravity and inertia are the same thing? Why? What is actually holding me to the table right now? What is causing that? What are my atoms doing to the atoms in the table right now? What are all of our atoms doing with the atoms in the floor right now to keep us held to the ground? So we don't know. I mean, that's a huge question. I think this is part of the void, and why I think this surrendering to the mathematics as the buck stops here is a really dangerous move for our civilization as far as science is concerned. Because yes, it's fantastic that we have general relativity. It gives us very precise measurements of what is, and very precise predictions of how different gravitational systems will behave. But we don't know why. We don't know the cause of it. And all of, people from Neil deGrasse Tyson to all of the popular science articles you'll find in the news, they do a really tricky sleight of hand where they'll reify this concept, this abstraction of space-time into a material and say, well, the material is warping, so the trajectory of the objects flowing through the material is going to be different. But this is just poetry. This isn't an actual explanation. You can't warp an idea in physics. In physics, only materials can be warped is the thing. And space-time's not a material. It's just a nice poetic analogy for what might be happening. So we don't have a solution to this problem. And kind of the tragic part is very few people are even working on that solution to the problem right now. We just have really good equations to describe how these things go down. We can explain how light works. Well, can we? We can describe how light works really, really well in terms of equations of electromagnetism and all of Maxwell's equations. And the same goes for gravity. Really good equations, really precise, but absolutely no explanation for what the heck is going on at the atomic level. And I think we'll be able to get by for a while like that. Of course, we have incredible technological progress in our modern civilization, but we may have reached a limit with it too, right? There might only be so far that we can go without actually interrogating the mechanism for how the atoms are pulling on one another and so forth. And it gets worse too. A result of Einstein's theory of general relativity, and more specifically his special theory of relativity, which is intimately related, is that time, the variable, is introduced. With respect to acceleration, obviously, in these Newtonian equations we have time as well, because it relates to the change of the velocity over time. So time is a natural variable inside of the Einsteinian equations. Now, the question becomes, what does time mean? What does it mean to Einstein when he's formulating these equations? Well, the answer is it means what his measuring system does. So it's what a clock does, essentially. And I think that we've touched on this a bit before, but one of the astounding things, and I think your textbook brings this up, is that one of the tests of general relativity is often cited as GPS, but maybe a more formative example of that is that you take an atomic clock into space, and what you find is that the atomic clock, as it's farther away from the mass of the Earth, as it's farther away from this heavy body of Earth, that the clock actually speeds up. So when that atomic clock is down on Earth, it goes slower. And of course, the popular media is very quick to be like, wow, time itself slowed down. But I think there's a much more reasonable interpretation, which is that, of course, clocks are affected by gravity. And the best example I can think of for this is the pendulum clock. Because if you take a pendulum clock out to outer space, time stops completely. And so inside of the Einsteinian equations, there's no difference between what a clock does and what time is. That's how you define time in the Einsteinian worldview, is by what clocks do, right? So the fact that a clock would be proportional, particularly a really, really accurate clock, like an atomic clock, that the atom would somehow vibrate differently away from all of the pressures of gravitation makes perfectly logical sense to me, and there's nothing spooky or supernatural about it. And certainly the abstraction of time itself isn't affected. It's just that your measurement system is being affected by the gravity on Earth in a way that it's not when it's away from Earth. So we have to be really, really careful with these concepts, and as tempting as it is to try to bring this almost supernatural fascination into physics, I don't think it's a good place for it. And that's why I spend so much time in this course talking about mythology. Because I think mythologies, and particularly this is the way our ancestors saw the stars, is a really, really valuable way of approaching these meta-phenomenological processes, these superstitious ideas in a way that's actually valuable to us. It actually teaches us about how to live. I think that putting supernatural ideas into physics is just a nightmare, because it's not going to lead to any kind of technological progress at the end of the day. It's just going to be a sucker trail that we get lost on. And I see a lot of that happening with respect to general relativity, and I think it's going to change drastically. Actually, I have a feeling that 100 years from now, maybe it'll take 1,000 years, but let's hope not. I think that the way that they will talk about the way that we thought about physics in this age is going to be very similar to the way that we talk about the way our ancestors thought about physics, where we are a little bit like, yeah, they didn't really understand how things worked. And they're going to think of us as a little bit like superstitious dum-dums a little bit. That's what I think. I don't know. I'm not going to be around to find out, probably. Okay. So one of the other consequences, of course, of general relativity, and as a result of that, is that, you know, as the reason that these bodies move the way they do is because the actual space itself, the coordinate systems, are somehow affected by the masses. Like, it's a very circular reasoning in some sense, that space, the coordinate system, is affected by the size of the bodies near it, and the size of the bodies affects the way that the space, which is just the distances between the bodies, is being warped somehow, right? And so the result of it is that you have this kind of a circular description of what we already knew, which is that bodies go around other bodies, which is absolutely apparent. So it's a very precise description of what was already apparent for thousands of years. Certainly was apparent since the idea of gravity was introduced by Newton in terms of this force. One of the consequences of that is that because the coordinate system itself in Einstein's model is bent, that light itself should be bent around these bodies. Now, this is also a really, really interesting and I think controversial idea. Your textbook has this picture, I believe. And this is, in some sense, at a surface level, very well accepted in modern astrophysics, that light is bent by extraordinarily large gravitational systems. One of the first tests of general relativity, actually I would say the first test of general relativity, was done by this gentleman, Arthur Eddington, who's come up a few times. It's actually interesting if you really dig into the story of Einstein. So Einstein was a German right around the time of World War I. Now, I don't know if you guys are aware of this, but people in the West did not like Germany right around World War I. They didn't want to hear anything from the German scientists. They didn't care for their ideas. There's a lot of really interesting political, let's say, back end to that story. I don't think we would have ever heard about Einstein if it hadn't been for Arthur Eddington. So Eddington was, what he did was he actually he was fluent in German. He read Einstein's papers and thought, this is actually really cool. This is a cool idea. Translated the papers. He actually wrote a popular blurb in the super high-impact journal Nature at the time, outlining the basic premise of it, and then proposed a test to prove that this was the case, that general relativity was the best and most accurate way. And he did that by way of the bending of light. So what he did was he organized two expeditions, and they were in the distant reaches. They had to basically go and find the next solar eclipse that was happening. And they went out there and they waited until the moon had essentially covered the sun. And then they were able to see stars that wouldn't ordinarily be visible right next to the sun, essentially. And what he did was he found that the stars that were right next to the sun, that their position had changed slightly. That it wasn't, the stars weren't where they used to be, let's say, regularly during the nighttime. They had been moved a little bit. Their appearance had moved a little bit as a result of it. And so, hurrah! Einstein has shown that light itself is bent because the space-time is warped and all of this. Now, it was actually a pretty crummy experiment. The accuracy was something on the order of 20%, which would never pass in a journal today. But we have shown since then that this experiment can be repeated with really tight accuracy. What's really bizarre, though, about this experiment, and this was, to my knowledge, all this work that I'm about to leave you with was done by this one NASA scientist named Edward Dowdy, who's no longer with us, unfortunately. I would love to talk to him. He points out a couple of really interesting things, though. So, one is that light only appears to be bent in the plasma limb of the sun, so in the actual atmosphere of the sun. Now, this is bizarre because we should, according to general relativity, there should be actually a slow tapering of the influence of gravity on light as it moves, several AU outside of the sun. So almost out to the Earth, we should see some sort of warping of the positions of stars, which we don't see. So that's really strange. Now this got Dowdy thinking that maybe it actually had more to do with the atmosphere of the sun than it did with anything related to space-time warping or anything like that. Now, another thing that Dowdy points out is that we see there's these things called Einstein rings. Maybe some of you have seen these in the popular media, where we see a large star that appears to be warping the picture of a galaxy behind it that's bent around it. You can see these in the Hubble Deep Field. The weird thing is that there's only a few of them, right? But general relativity predicts that essentially every large star should be warping the space around it in such a way so that we should see little lenses around literally every single star. In fact, most of the stars that are in between us and the stars, because we've talked about this, that most of the stars that are close to us we can't even see because they're dim. We can only see a couple of the stars. Literally, the night sky is just packed with stuff. Why is all that heavy stuff not lensing everything? Why don't we just see complete optical craziness everywhere in the sky? So that seems a bit inconsistent as well. He also brings up the point that we're supposed to have this supermassive black hole at the center of our own galaxy. But we don't see any lensing associated with that whatsoever, right? It's just a big, bright ball at the center of our galaxy from what we can see. So, and Dowdy actually proposes a really interesting, he was a plasma physicist, and he proposes a really interesting lensing effect due to the plasma in the limb of the stars. So, as far as I can tell, the idea of whether light is bent by gravity is completely up for grabs. The only examples that you'll find are these astrophysical examples. We can't do it on Earth, right? You can't shine a laser and have it be bent by the mass of the Earth for whatever reason. So, anyways, let's conclude this with saying that general relativity chops up the world into space and time, which prove extremely problematic because we've departed from actual material explanations as we had maybe closer in the time of Newton. And this is going to tee us up for considering what happens when we cross the threshold of those equations into some extreme conditions. What would we expect to happen? And we'll talk about black holes on Thursday. All right, guys, have a good week. Hey, if anybody wants to come early Thursday, I'll hang out. I'm not going to make any coffee because nobody's drinking it, but we'll have something of a hangout / office hours, whatever you want to call it.